Okay, yes, so my talk is about mantle structures and their origin. And I wanted to say first, thank you very much for inviting me to give this talk. And this time I decided not to join in person in order to save on CO2 emissions. And of course, I will be very much looking forward at some point to come again in person to Sendai. This picture shows me, for maybe some of you may remember, that I came visiting in Japan in 2017 and I gave a talk in 2017. And this picture shows me together with my daughter, who accompanied me at this time and who also contributed some of the cartoons I will show in this talk. So not this one. So yeah, so structure in the mantle, it's basically, well, what we know for sure about the mantle is that the mantle is convecting, and because basically that's the only way of how the Earth can get in a reasonable way get rid of its heat. And both experiments and observations indicate that it's in a form of plate tectonics with slabs going down to the mantle, some of them continuously, some of them stagnating in the transition zone, and there are plumes coming up. Again, there is some evidence that they may not all come up straight through the mantle. And yes, so those are the basic structures. Those are the thermal structures. So about thermal structures, what we know for sure is about slabs and plumes. And then there is also most likely chemical structure in the mantle. This chemical structure is created through melting, which separates material and creates crust. And then this crust goes down with the slabs, and it possibly accumulates at the base of the mantle in piles in the so-called large low shear velocity provinces. So these are the different chemical structures. And through the mantle convection, through this mixing, the chemical structure is also continuously being erased again. So again, a mantle contains thermal and chemical structure. Convection creates the thermal structure and erases the chemical structure through mixing. And melting separates material and causes a chemical structure. And where the large uncertainties of mantle convection really come in is that we know very little about mantle rheology. There are many ideas, which some of them I will propose, but very little consensus on mantle rheology. So this is where the large uncertainties come in. And now I will go in a bit more detail through the individual points, through the individual aspects of this convection and structure. So yeah, so the best tool for knowing about the mantle is obviously seismic tomography. There are also electromagnetic methods, but mostly seismic tomography. I will show results here. And what is best imaged by tomography is subducted slabs. And here I show two cross sections through a tomography model. This is this Texas tomography model. And in this particular model, slabs have been included in the starting model. So that's why they show up very prominent in the upper mantle. But then you can see, yeah, for example, this cross section through Japan, which I'm sure everybody know about other models of this, that there is the stagnating slab here. So it doesn't immediately penetrate to the lower mantle, but there's also slab material in the lower mantle, indicating that the slab will go down eventually. Then if you have here this cross section under South America, it's much more continuous. So there seems to be continuously going down. Right. Here, since I'm from Europe, here showing another stagnating, what looks like a kind of a stagnating slab in this Utrecht tomography model from a north-south cross-section through Europe, which lies flat under Germany, where I am right now. Right. Then I think what I can contribute a bit more from my own work is the lowermost mantle. Then when the slabs sink into the mantle, you can see this is the subduction locations through time, where the color corresponds to time in million years and the intensity, how much has been going down. So there is basically this ring around the Pacific, or formerly Panta Lassa, where subduction has occurred. And this ring corresponds very well with where you see fast seismic anomalies in the lowermost mantle. And where those fast seismic anomalies are not, these are the regions where you have those so-called large low shear velocity provinces at the base of the mantle. And then the upwelling part of the mantle flow, the plumes, they focus, or they are mostly located in the regions of those large low shear velocity provinces. And also, as you can see, particularly well around Africa, that they tend to be along the margins of those large low shear velocity provinces. Right. And yeah, so the question now, or one still unresolved question, is whether there's really the slabs are that they push the thermal and maybe chemical material away at the base of the mantle and create those LLSVPs where they are, or whether they are stable by themselves, or whether they dominate the dynamics and are stable and influence that subduction can only occur away from them. That would be this mantle anchor structure model, which has been proposed by Adam Dzivonsky about it. Those upwellings are really in charge. And I think most people would rather think that the slabs are what dominates the structure because the surface is bigger. But then the question is, as I will come back in a moment, why those LLSVPs seem to be so stable. Right. So about what those LLSVPs consist of, so there are basically two different ideas. That is, one is that it's primordial material has been there since the beginning of the Earth, and the other it could be that it's a subducted slab material that's accumulated over billions of years. And this is just to show this is these are images from a model run by Elvira Muliokova during a PhD she did with me. And when you have the color showing the different, I think, color showing the amount of crustal material. And when you look at in detail at the slabs going down, there is part of the slab is crust, and at the base of the mantle, this crust tends to get separated from the rest of the material because it's heavier and tends to partly accumulate in piles. And over 3 billion years, you can accumulate enough material to generate the size of the large low shear velocity provinces. Now here is a bit of more detailed view of one of those piles in the models. And you see there are plumes forming at these cusps near the edges of those piles. And there is again material being entrained in the plumes. So there seems to be some both material being added by the slabs and then material being taken away by the plumes again. And there are also models and observations which show that this material from the piles, it may be only on one side of the plume. So there is this idea of zoned plumes, that on one side of the plume, material from the pile comes up, and on the other side, it's primarily ambient mantle material. So there are chemical observations from a number of plumes right now, which would indicate this. Right. Now, the dynamics of why plumes form along those margins of the piles is, for this I had a paper with Trond Torsvik in 2012. And the basic idea is that the slab just pushes the thermal boundary layer at the base of the mantle, and at the same time pushes the chemical material and forms them into piles. And at the margins of those piles, those thermal material is being forced upward and generating plumes. So this is a numerical experiment, cross-section here and map view here in violet showing the domes of chemical piles, in these red-green colors showing where the plumes come up near the margins of those piles, and those bluish colors showing where the slabs are going down. So that, again, shown in this cartoon, slabs going down and pushing plumes, and the plumes rising at the margin of those piles. And with time, maybe the source of the plume moves towards the interior of the pile. And what's also important, that because this is not an empty space, but there is material in between, the slab starts already pushing. Once it's in the mid-mantle, then it has enough force already at the base of the mantle to push the material ahead and generate plumes. So this is about the ideas about the interaction of slabs going down and plumes going up. Right. Now, where those plumes are located, again, if you look at the location of hotspots at the surface, they tend to, especially very well visible above the African LLSVP, they tend to form along the margins. And this is a figure, I think, from this distinction between primary clearly resolved and somewhat resolved plume is from a recent paper by Romanowitz et al. So the primary plumes are the ones which they see coming up through tomography from the lowermost mantle, and clearly resolved also, mostly likely from the lowermost mantle. And those tend to be all associated with the piles and especially with their margins, which is especially well seen on the African side. Now, in order to go back in time, we don't only look at plumes, but also at the large low shear velocity, now at the large igneous provinces, which are probably corresponding to the big heads of the plume. And when you reconstruct them to the places where they originally come up, then you find also that they tend to be, the reconstructed locations tend to be along the margins of those piles, similarly to plumes, right? Because many of them correspond to plumes. And then if you reconstruct, for example, Deccan, which is now here, DT Deccan Trap, to where it originally erupted, it comes here at the margin of the African large low shear velocity province. So because you can do this back in time, those large igneous provinces erupted during the last 250 million years. So you know that they must have been, those piles must have been stable for at least 200 million years, and they could have been stable for quite a bit longer. So you can, further back in time, you have some uncertainties in longitude with the reconstruction, and you can adjust the longitude such to make it fit even older large igneous provinces fit along the margins. And for the last 200 million years, the stability of those piles can be quite easily explained because the slab, for the last 200 million years, the slabs have been going down in this region, so they would naturally push the piles to here. And the longer stability is somewhat more difficult. Then you would have to think of that they're somehow inherently stable and keep the slabs maybe away from them. But that's something still in work to see whether they have been stable for much longer. So this is much more uncertain. Then, so then once the plume comes up, they will interact with the lithosphere. So the simplest case is for Hawaii. Here is a cartoon showing that there is this stationary plume head forming under the lithosphere as the plume spreads underneath it. And at the center of it, you will create a hotspot track. Now, what's special about the Hawaii is that you have this bend in the Hawaiian chain, which probably corresponds to a change in plate motion, maybe also some hotspot motion. And the thing is, when you have this bend, then you have this plume head being sheared by the, so in this case, it's just being sheared in the direction of plate motion. But when you have this bend, then it tends to get sheared sideways. So this plume head gets shifted sideways from the actual track. And that's something which we actually have an experiment which has now been granted together with Baba-san, where we will use ocean bottom seismometer and ocean bottom electromagnetometers to look at this region here to see to which area this material from underneath the emperor chain has been moved. So there should be still something visible, and depending on where it has been moved, it can tell us something how well this material is coupled with the lithosphere. And so this can tell us something about the mantle viscosity structure. So I'll come back to this because, as I said, mantle viscosity is something which is very poorly known. And so anything which tells us more about mantle viscosity structure will be welcome. So there will be 2 cruises for deploying and collecting those ocean bottom instruments, one from Germany and one from Japan. and that will probably happen in 2024 and 2025, which I'm not sure about yet, or 1 year later. Yes. Yeah, so more about plume ridge interaction. Plume lithosphere interaction is this example for Tristan. When you have a plume close to the ridge, then it won't only form this kind of focused trail, but you will have material flowing from the plume towards the ridge, and you will have more of this kind of distributed trail. This can be seen here. They have several like parallel strands of hotspot track, and then later on it gets more focused, which probably means that at this time the plume was situated right below the ridge. Now, even more complicated is for Iceland. You don't see any real track here, but you find volcanism here at the west side of Greenland, at the east side of Greenland, and we have written a paper trying to explain this through through the interaction of a plume with a moving lithosphere of variable thickness. So the idea is basically that the plume was for a long time under thick lithosphere and a lot of material accumulated. And then later the lithosphere moved over it. And there was at the same time was first spreading here. Then this material, which had accumulated there for a long time before, came to the surface at a time when the plume was already here. And then here the North Atlantic opened, and and there was also a lot of volcanism there. Okay, now coming to imaging plumes and how they compare with observations. So showing for Iceland, you can see in this, again, the Texas model by Liu et al. Can see something which, of course, cross sections only show cross sections and don't show what it looks like in 3D, but at least this cross section is very, I think, quite convincing to show the plume. It maybe also shows some spreading in the transition zone, but it's continuous hot anomaly from the base of the mantle to the top. And it also shows that the plumes seems to be quite fat. So the plumes tend to be fatter than you would imagine if they were purely thermal plumes. Right. Just how far am I in time? Is it 15 minutes now or?
15 minutes.
15 minutes, okay, then I have time. All right, so this shows the idea of how a plume conduit gets deformed. So because they maybe not all come out straight, so you can look at them through tomography, and you can also model how plumes get deformed. So from 1 to 6, first the plume head starts rising, and while it starts rising, it gets moved with the flow, and at the same time, the plume conduit also gets moved with the flow, and the plume conduit rises less fast. So due to interaction with possible large-scale flow, the plume conduit will get tilted and deformed, and you can predict that there will be this tilted plume conduit. This is just an example showing under North America. Here's North America. Here's Yellowstone. So you would have in the lower mantle, you would have flow towards the center of the Pacific. So the base of the plume would get moved this way, and in the upper mantle, it wouldn't get moved. So you would expect a tilted plume conduit for Yellowstone. And that's, again, depending on how fast the plume head rises. Excuse me, go back. If it rises slower, you get more tilt. And in this case, you find you need about 120 million years for the plume head to rise. Then you get the base of the plume situated under Southern California, the top situated under Yellowstone. And there is also this tomographic image by a group of Steve Grant and Peter Nelson was the main author, which shows also a tilted plume conduit, which roughly agrees with what we find with our model. So if you have a large plume head rising time, you can get both the amount and the direction of the tilt right. So for this case, it works quite well. for other cases, it kind of works, this prediction. But for example, Hawaii, this is a predicted plume conduit. The base of the plume, this move towards the center of the Pacific. This is the observed plume. It's also slightly tilted, but somewhat less, right? And here you can imagine that this is the large low shear velocity province at the base of the mantle, and this is the plume. So it would have been generated here, but with time the plume source might have moved towards it, and now it's this tilted plume conduit, right? Looking at other ones, this just show another tomography model where you can see this particularly well. This is the Reunion plume, another prominent plume, and here you can see this very massive African large shear velocity province, and again the plume seems to rise from its margin and being tilted outward in more similar way as what we have observed through what we have predicted. Right, there are other plumes like Comoros where it also looks good, and what is seen here is particularly that there seems to be very strong tilt or deflection somewhere around 1,000 kilometer or at the upper part of the lower mantle. So that's something which this tomography model shows, that often plumes don't come up straight, but in particular in this region, they tends to be tilted. And this model tilt tends to be a bit more focused in this depth range than now the observed tilt in tomography tends to be a bit more focused than what we model, where we model more or less a continuous tilt. So this is an example for St. Helena, also at the margin of the African large shear velocity province. Another one, so Canary Island also seems to be a continuous plume, again showing that at least in the tomography model, it tends to be very massive, very fat. And the question is why this is much fatter than you would expect for a thermal plume. And so there are ideas that this is basically maybe contains a lot of chemically different material and has more difficulty rising to the mantle. So you need this massive and fat plume in order to come up. But these are all things that are still under investigation and are not agreed upon. Right, so as I said, the largest uncertainty comes from mantle viscosity. So radial viscosity, here in this case, which I did together with Arthur Calderwood. What you know from post-glacial rebound is kind of the average viscosity through the mantle and a little bit of depth dependence. So you know this average value of about 10 to the 21 Pascal seconds. And from modeling the geoid, that you have both geoid highs above low density material in the lower mantle and high density material in the upper mantle, you know that you have to have a strong increase of viscosity of about a factor of 30 to 100 or so between the upper and the lower mantle. And another indication is that those hotspots tend to move very slowly, so they need to be anchored in a high viscosity lower mantle. So those are things which I can tell you about the radial viscosity structure. As I said, we have now funded this cruise under the Pacific, which can tell us more about the radial viscosity in the mantle under oceans, under the Pacific, depending on how plume material is coupled to the lithosphere, can say something about how the viscosity varies with depth. Right, then besides radial viscosity, you have probably temperature-dependent viscosity. This is showing here from a paper by Lin and Van Keken. This is a constant viscosity, a rather wide plume, and the plume tends to get narrower with temperature-dependent viscosity, as you expect for the plume. The thing is that, as I said, the plumes, according to the seismic observations, they tend to be rather wide, which is somewhat counter to what we expect for thermal plumes. Right. Then, besides temperature-dependent viscosity, there may be composition-dependent viscosity. And there is this idea of this bridgmanite enriched ancient mantle structure by Balmer and co-authors, showing here different composition, different temperatures. And here, what does this show? Viscosity, yes. So because bridgemanite tends to have higher viscosity, so you tend to have these regions of very high viscosity in the mantle, which don't mix well with the rest of the mantle. And in this particularly case, these regions are actually, that is, are blobs which are sort of rotating in the mantle. And most of they tend to be not mixed with the rest, they just rotate fixed. And you tend to have in between the flow of plumes coming up and of slabs going down. So yes, so this is about, yeah, so the cartoon view again is that you have this rotating high viscosity materials. You have in between, you have the piles of large shear velocity provinces with plumes rising above them and maybe above their margins. And then at other locations, the slabs going down. And at map view, they suggest that you have where those arrows are, where you have this indicating the upper mantle flow. This is where underneath are those what they call beams, bridgemanite enriched ancient mantle structures. Another idea is that it's also viscosity may be strain rate dependent. So it may not be that this is bridgemanite enriched, but it's just that in these regions, the bridgemanite is interconnected and then the mantle is stronger. However, if there is strong shear in the mantle, like in the plumes or in the slabs, this leads to that the much weaker magnetio-wustite gets interconnected, and then this load-bearing framework of bridgemanite gets destroyed and you get much weaker viscosity. So in this case, viscosity dependent on strain history. Right, and then finally my summary, again, that I said that thermal structure is created through convection. What we know is slabs going down and plumes coming up can be reasonably sure. And chemical structure gets created through melting. And it probably accumulates at piles at the base of the mantle, and it perhaps also entrained in mantle plumes. And it may be some of this chemical structure may be ancient, primordial. So for example, in the piles, and perhaps also in this bridgemanite enriched ancient mantle structures. And the complication of where we still have large uncertainty of what's going on in the mantle is about the rheology, because viscosity, what we know for sure, it's depth dependent, and most likely it's temperature dependent, but it may also depend on composition. It may depend on strain rate, and also strain history. Okay, thank you very much.